flat.
Yeah, we're good.
Hey, Brandon. Part 2, we're developing equation number 3. We have a velocity time graph, and the velocity initial is marked where the velocity is already, there is a velocity of this object at the beginning, and it's marked theoretically right there, and the velocity is actually increasing, and I'm going to cut it off at time t. So sketch that on in your development on equation 3. All right. We're going to divide that. Can you divide that most easily? Oops, that probably jostled
I was
there.
moving it.
Sorry, Brandon, I hit the table. I want you to divide that into 2 geometric shapes, one a rectangle and one a triangle. So how can you most easily do that? All right, as she has chosen the correct spot. So if you recall, when we learned in the middle of the last mod with weeping, we noticed that the area under the velocity curve was displacement. So displacement is going to be represented with an x. So over here, Emily put x equals, and so we're going to find the area under that curve or that straight line. So we divide it into a rectangle and a triangle. So geometrically, Emily, what is the area of this particular part of our graph, just the rectangle? Any rectangle is going to be length times width, so we want this value times this value.
Velocity initial times time.
Right, and would you write that right inside the box, V sub O? The area of a rectangle, and this particular one is its height times its length. So would you write that here, V sub OT plus, now we got to do the triangle, so that's the rectangle. Go back to the triangle part and see if you can come up with, do you recall the area of a triangle? 1/2 base times height, and so what is our base in this case? So write down 1/2 in here, and then what's the base? Time. And what is the height of just this triangle part? All right, since I cut the problem off here, we can read the final velocity up there. So what is just, final velocity. So add the little v at the very peak of the travels of our object right there. So I need this height. So can you look at this graph and tell me if this is v and this is v sub o, what is just the part on the triangle?
V minus V sub O.
Exactly. So in parentheses, next to the t, write v minus v sub o. All right. So when you transfer that over here, when you get to v minus v sub o, just call it change in v. So we'll do 1/2 t, and when you get to the parentheses, just do little triangle, change in v. All right. All right, over underneath of that, I want you to give me the acceleration equation again. So acceleration is change in v over change in t. And I want you to solve that for change in v. All right, now I'm going to substitute and change in time, because time is always starting at 0 in almost every single problem. I want you to rewrite this. Instead of change in t, just call it t. So you want change in v equals at. And I'm going to take this value and substitute it in for change in v up here. So if you would start here with x equals, when you get to change in v, put in at. Substitution. All right, so she's got a t here. Where's the 2? We have a t in the problem here. And then she put in another at. So clean that up. We have a t times t. So down here. And that should be her last step. All right. Very good. That's it. Thank you, Emily. All right, so this is our grand finale, and we're going to make a note about it. On the first one, we noted there was no information on distance. On this one was no information on time. What kind of information is missing on this one? Can you see it? What's missing on this one? No info on, Emily Davis?
The velocity final.
Right, no info on final velocity. So at the end of the story, we don't know the velocity in the problem and it cannot be calculated. So that would be a good clue on using that equation. All right, memory aid. All right, my memory aid for this one is my most excellent advice to you. That's where the word excellent, the word excellent tells you that we're working in X. Alex, listen to the memory aid. The most excellent advice to you is to vote. You see the word vote? V sub OT. And half I'm going to say as have at it. So when I say at it, you hear T twice, that tells you to square it. So my most excellent advice to you is to vote and have at it. That's my symbol for have at it. My most excellent advice to you is to vote and have at it. All right, say that with me. My most excellent advice to you is to vote and have at it. All right, so I'm very attached. The very worst squall is the very first squall, and it comes like two X's. My most excellent advice to you is to vote and have at it. All right, we'll go over those from time to time and see if it helps. You will not be able to bring those with you to a test, so if my memory aids don't help, you have to come up with your own. So, all right, this will lead us to example. Brandon, you have these papers. I gave them to you yesterday. Example 2.3, and that is about a plane. So I remembered to keep the picture off so you get to draw it. A plane, a plane, a plane. Alex, would you read it? Example 2.3, a plane starts.
The plane starts from rest and begins to accelerate down the runway at 2.3 meters per second. If it takes off in 28 seconds, how far does it travel down the runway?
All right, use our new equation, our voting equation. The most excellent advice to you is to vote and have, that's for have at it, at AT squared. A plane starts from rest, so we need a plane. Draw a plane starting from rest. Indicate with an arrow that it's accelerating. 2.3, so it's getting faster and faster. It's a positive acceleration, and it's going to lift off somewhere in 28 seconds. At what point? How far down the runway is it before it lifts off? So see if you can work that
Miss Bell,
independently.
how many equations will we be deriving?
3.
Just 3 times.
Alright, so on this example, you have the plane, not too interesting of a picture, not as dramatic as the last one, just the plane lifting off. What numbers are coming up where? Thunder, help me with that. Do you see some numbers you can grab from that problem and stick in where?
So we don't know X.
Okay. So that's what we're looking for is it, yes, we're looking for when, or at what point, how far down the runway. Do we know velocity initial? What's the jet doing at the beginning of the problem?
Starting from rest. So
See.
the initial velocity is 0.
Alright, so 0, and then time, it doesn't really matter in this step what time is, but we'll put it in. What is it?
28.
Alright, but it doesn't matter because 0, it's going to 0 out anyway. So anything starting from rest, that term will go bye-byes.
So
1/2, and acceleration, Hunter,
2.3,
and then the time again.
28 seconds.
Right. And we have to square that as the formula does. So it's just not even something to solve, it's just a plug and chug. What is 1/2, 2.3 times 28 squared? We're gonna take 2 sig figs. So, do we have a number? Hunter, when you get it? Just give me the number and we'll work on the sig figs together.
Well, the number is 901.6.
All right, so that we were working in, what were we working in? Meters. So how do I get that to 2 sig figs? I see that my 28 had 2 sig figs, my 2.3.
It would just be 900.
It would, but that communicates to the reader only 1 sig fig.
So you
this,
point.
and that would communicate 3 sig
So
figs.
you just leave it as it was.
And so you really have to tell the reader somehow. Ideas?
You could do 9.0 times 10 to the
Oh,
Right.
that's right.
Right, you can, I have seen this as well, this kind of weird, but it kind of tells the reader I'm counting this as a sig fig and not this, but that is really, I haven't seen that very often, but I have seen it, and then 9.0 times 10 squared using scientific notation. I didn't teach that this year because I assume you come to me knowing that, so if you don't, I will sit with you and go over that. But 9.0 times 10 is 900, and that tells the reader, 9.0 times 100, 10 squared, is 900. So this is the same number, it's just written this way so you can clearly see the 2 significant digits. All right. Let's take some time, and the 5-minute bell is going to ring. It'd be nice to get our on your owns finished before class ends. So if you would look for those other 2 on your owns, Alex, you'll be able to do them now. So I just want to say goodbye. So Brandon, we're going to work on the on your owns 2.2 and 2.3 using the equations from today's class, so there won't be any other homework other than that. Tomorrow we're going to come in and practice, practice, practice. You won't know which equation will go to the problem, and you'll be able to pick it out and work it well. See you then.